Sorry, can I ask a quick question? So on the Slack, I see the Zoom won't let us in. It has the wrong date as a comment. Is that just because we haven't started the webinar, or is there something fishy going on?
Okay, I'm back and we're streaming. Luna, go ahead and try one more time.
Sorry.
Are you all set with the Slack?
I'm all Slack set, but the Slack has a comment saying that the Zoom won't let people in and there's a wrong date. Is that just because we haven't started the webinar?
Oh, no, there's a problem. There must be a problem because the attendees are not here. Where is the wrong date? Is it on the...
So I just have a comment. Sorry,
I believe that they can't, sorry, I believe that they won't be able to join until 12:15. And so if they tried to get in earlier than 12:15, they'll get a notice that it's not.
No, that wasn't it actually. The problem is that I missed a button, but I just clicked it. And so hopefully, well, let's see. Yeah, the webinar has started, but I still don't see any attendees. But hopefully they'll start filing in momentarily. Yeah, here they come. Okay. So we'll give it a minute, wait till everybody gets here. We've got one attendee. Susanna or Tharni, maybe you could check the program. Is there something wrong in the virtual platform? Is the link to this press conference not in there or not correct?
I can see the button to join, and it did open a launch meeting tab when I clicked on it.
So I think, so in the chat, it says it becomes active at 4:30 p.m. on June 9th. Oh, so I think there's a mix up with the wrong webinar Zoom maybe.
Okay, yeah, that's the problem. Sorry about this, everybody. Let me get the correct link and let me make sure I send it to the help desk and ask for hopefully instant help. All right, stand by. All right, for those handful of you that are here, we appear to have the incorrect link to the press conference in the VFairs platform. So I've sent an urgent request to get that link corrected, and hopefully it will. I see we're not the only link that's bad. Okay, the link has been corrected. So if you refresh that page, hopefully it will take you to the right place. Can you throw that in the Slack, Luna? Let everybody know that they should refresh VFairs and then click on the right link to the press conference.
Susanna beat me to it.
Great, excellent.
Well,
okay.
I said try again, but I don't know if more instruction is needed.
Well, of course, you put it in the chat, right?
No, I put it in the Slack.
Put it in the Slack? Okay, great, great. All right, we're getting more people, so. All right, here comes people. All right, we're going to just wait another minute or so and give people a chance to get the correct link and join us here. I'm going to go ahead and begin the introductions, and it's not critical if some people don't get here till after the introductions because the program lists who's speaking and what the topics are, so that's okay. So go ahead and stop sharing if you don't mind, Susanna. Hello, everyone. I'm Rick Fienberg, AAS Press Officer, and I'm excited to welcome you to the first press conference here at the 238th American Astronomical Society meeting. We're coming to you from all over the place, virtually, of course, and hoping that this will be the last time in the pandemic that we have to do an all virtual meeting, though it's great to have so many people joining us for a summer meeting, including a turnout of journalists that is more like a winter meeting. We have about 100 journalists and public information officers attending, which is really remarkable for a summer meeting. So we're getting a slightly late start because we had a bad link in the virtual platform. I'll double check that all the other links are correct before the next briefing. And I apologize for the slip up. It's hard to keep track of everything that's happening the last day or so before the meeting actually gets underway. So let me introduce you to all these faces that you see smiling on your screen. So first of all, I'd like to introduce my press office staff for this meeting. In addition to myself, we have Susanna Kohler, who is the editor of AAS Nova. And if you saw the announcement from the AAS a few weeks ago, she's going to be taking over as press officer from me when I retire in September. She'll also continue to manage the AAS Nova website and do a bunch of other stuff. Assisting also today is Luna Zagoratz. She is the Astrobytes media intern who's working with us this week. She's a graduate student who writes for the Astrobytes blog, and that contributes also to AAS Nova. And Susanna is going to be monitoring the Q&A today, and Luna is going to be monitoring the Slack channel. If you don't have the Slack channel yet, you can add it by clicking the add button or the plus sign or whatever you have on your Slack app, and add the press conferences channel. Like all the other channels, it starts with a hashtag. And then the AAS Media Fellow, who is finishing up a 2-year term helping Susanna and me, is Tharini Konchadi, also a graduate student who has also written for Astrobytes, and she's closing in on her doctorate. All right, so today's topic is stars and clusters. We'll have 5 presentations. The reason you see 6 presenters is because for the first presentation, Auroral Electrons Surfing on Alfvén Waves, James Schroeder from Wheaton College in Illinois will be assisted by Gregory Howes from University of Iowa during the Q&A. Next up, we'll have Mind the Gap, Observing the Jet Coronal Mass Ejection Continuum, and that will be presented by Emily Mason, who's affiliated with both University Space Research Association, USRA, whose logo you see behind most of us. We thank them very much for their sponsorship of the press office at this meeting. And Emily's also affiliated with NASA's Goddard Space Flight Center. The third presentation will be given by Peter Garnavich from the University of Notre Dame. His title is Confirmation of a Second Propeller, a High-Inclination Twin of AE Aquarii. Fourth presentation will be Eta Carinae's Change of State as seen by Hubble from 1998 to 2021. And the final presentation at this morning's briefing, or this afternoon's briefing, if it's afternoon for you, is an open cluster spread across 1,500 light years by Luke Bouma from Princeton University. So just to make sure everybody knows how our AAS press conferences work, in case this is the first time you've attended one, we'll have all the 5 presentations in order, one right after the other. And then when they're finished, we'll go to the question and answer period. We're using Zoom's Q&A feature for the Q&A. We're not using Slack for the Q&A. You can use Slack to kibitz with your fellow science writers and comment on how great we all look today. But if you want to ask a question, use the Q&A button, which you'll find probably at the bottom of your Zoom screen. And everybody has the ability to upvote questions. So if somebody asks a question that you were thinking of asking, you can upvote it and that'll raise it in the queue. If you see a question that you just think is a really great question, you can upvote it. And when we get to the Q&A, Susanna will read the questions from the top down. So the more votes something gets, the higher priority it has and the higher likelihood we'll have time to get to it. All right. So I think I've covered pretty much everything that I wanted to cover. Just a reminder to everybody that we are recording this session on YouTube and we're live streaming as well. All right, so with that, I'm going to turn it over to the first presenter, Jim Schroeder, and the rest of us will mute and take it from here.
Hello, my name is Jim Schroeder. I am the first author of a Nature Communications article published today about auroral electrons surfing on Alfvén waves. I'm also presenting the results of this paper for the first time here at the AAS conference. I'm joined today by Greg Howes. Greg led the theory side of this project and will share the microphone during the question and answer part of this session. Together, we prepared a packet of information that has the graphics you'll see in today's presentation, as well as a summary of our work, and that packet is available at this URL. I'd also like to acknowledge the support of NSF, DOE, and NASA. Without their support, this research would not have been possible. At the end of the chain of events that leads up to an aurora is the precipitation of electrons. Electrons come raining down from space and crash into atoms in the upper atmosphere. It's these collisions that lead to the emission of photons that make up auroras. But the question for decades has been, what causes electrons to precipitate? Or equivalently, what accelerates these electrons toward Earth? So this is a long-standing open question. It's also known that energy flows along Earth's magnetic field down toward the Earth. There is a constant stream of solar material flowing past the Earth called the solar wind, and sometimes also eruptions of solar material called coronal mass ejections strike Earth's magnetic field, distorting it, stretching it out, and storing energy. When this energy is released, as you'll see here, it can flow along Earth's magnetic field down toward the Earth, where auroras are produced. For over 40 years, Alfvén waves have been hypothesized to be an important part of explaining all of this. So when you think of Alfvén waves, imagine waves on a string. So if you take a string and shake one end of the string, you produce waves that travel along. Similarly, with magnetic field lines, if magnetic fields in the presence of plasma, like Earth's magnetic field, are disturbed, waves travel along the magnetic field lines. And so the idea is that when Earth's magnetic field is disturbed by the solar wind or coronal mass ejections, waves travel along Earth's magnetic field down towards the Earth, these Alfvén waves, and that much is known. But what's been hypothesized is that Alfvén waves transfer their energy to electrons that then precipitate to produce auroras. The reason why this has remained an untested hypothesis for so long is that it's really difficult with satellite data to identify if or how electrons are interacting with Alfvén waves. But what we do know from satellite data is that Alfvén waves are conspicuously present above many auroras, including some of the most brilliant auroras. So if I asked you to picture an aurora, what you would probably come up with in your mind is actually what's called a discrete aurora. So these are bands of light across the sky that wiggle and writhe around. And satellite data have shown us that Alfvén waves are especially present above these auroras. But what we haven't known is whether Alfvén waves can actually cause these auroras or if Alfvén waves merely occur alongside them. So we wanted to perform a direct test. To do this, we went to the Large Plasma Device, or LAPD for short. This is a collaborative research facility funded by NSF and DOE at UCLA. It's one of the premier places for studying Alfvén waves. And the goal was to see if Alfvén waves transfer energy to electrons in a way that would allow electrons to produce auroras. So this is an image of the LAPD. It's got a 20-meter long chamber. Inside that chamber, we produced Alfvén waves using an antenna. And 5 meters away from the antenna, we performed some measurements to monitor how electrons were energized and what to detect whether or not electrons were being accelerated in response to the Alfvén wave. Before I show you any results, I want to show you, put a picture in your mind of somebody surfing. So when I start this video, what you'll notice is that there is one person that catches the wave and then a bunch of other surfers that don't. And the distinction here has to do with initial velocity relative to the wave. So the one surfer that caught the wave had the right initial velocity to be picked up and pushed forward, accelerated by the wave. This is called resonant acceleration. And electrons are predicted to be able to do something similar in the presence of Alfvén waves. Electrons with the right initial velocity are predicted to be able to be picked up and accelerated by the Alfvén wave. So like these electrons shown schematically here. Meanwhile, other electrons that don't have the right initial velocity would be merely passed by. And so effectively what this theory is that it's that electrons can surf on Alfvén waves. Now, I'm excited to announce that our experiments showed electrons are accelerated by surfing on Alfvén waves. And this is the first direct measurement showing that Alfvén waves can generate auroras. Below is one of the key plots from our paper, from the Nature Communications paper. And what you see plotted here on the vertical axis is energy transferred to electrons. And on the horizontal axis is the initial velocity of electrons. So what you see is that electrons with these initial velocities are not gaining energy from the wave. Meanwhile, over here, electrons with these initial velocities are gaining energy from the wave. And it turns out that those velocities are near the velocity of the wave itself. So these are electrons that are being picked up and accelerated by the Alfvén wave. These are electrons surfing on Alfvén waves. And what we found is that they would gain enough energy through this process to be able to produce auroras. So now that we've answered this 40-year-old question, the next question is, what's next? And the answer is that there are a whole bunch of places in space and astrophysical settings where we would like to know more about how particles are energized. And the tools that were developed here can help answer those questions. So for example, we'd love to know more about how the sun's corona is heated to 1 million degrees. Or we'd like to know how cosmic rays get to have ultra-relativistic energies. Or also why there are belts of highly energetic electrons and protons around the Earth called the Van Allen radiation belts. Both Greg and myself would love to be contacted if you have any questions about this work, either by email or phone. And again, the package of information that we produced is available at the URL shown. Thank you.
Emily, you need to unmute your audio and video.
Sorry about that, everyone. Okay, so this is the Rosetta Stone solar eruption. So solar eruptions come in one of three types. There are jets, CMEs, and failed eruptions. Jets, on the one hand, are usually...
Emily, I'm sorry to interrupt, but are you sharing your screen? And we're not seeing it.
Must have turned off when I hit escape.
There we go.
Are you seeing it now?
Mm-hmm.
Okay, there we go. Okay. This is the Rosetta Stone solar eruption, for real. Okay, so solar eruptions come in one of three types, basically. You have jets, CMEs, and failed eruptions. On the one hand, you have jets, which are usually very narrow, pretty slow, and small eruptions that only send out narrow columns of plasma into the solar wind. On the opposite extreme, you have CMEs, or coronal mass ejections. These are much larger eruptions that can take up angles that encompass the entire sun or more. They get much larger than the sun as they expand outwards, and they eject both plasma and magnetic field, which give it this lovely kind of structure that you see, that bubble-like shape. But despite this huge range of observational characteristics, it's been hypothesized for some time that there are actually both just two ends of a continuum, that the same underlying mechanisms are driving eruptions. And the event that I am showing here is kind of the missing link. It connects the two ends of this jet to CME eruption continuum. So why this eruption? This eruption shows characteristics of all three types in one neat little package. You'll see here that this structure has kind of two components, and the eruption itself has two components that go with that. There's this nice, hang on a second, let me switch over to the laser pointer. There's a dome here, a dome-like structure up and higher in the corona, and down near the surface is this long, darker structure called a prominence. And each of these erupt in different ways, and they give the two components of this eruption. And this eruption gives us a lot of physical insight to open questions about eruptions, like how do you get each different kind of eruption? What does the surrounding magnetic field around a structure like this have to do with what the eruption looks like? And really, why structures like this even erupt at all? So we're going to look at this eruption from several different angles. We were lucky in that stereo was well positioned to observe this from the opposite angle, basically almost exactly opposite from SDO. SDO orbits the Earth here, so it's here in this diagram. Stereo A was positioned here, and the event was basically right between the two. So we got to see both the front and the back end of this structure. So I'll show data from stereo A showing the eruption. I'll show data from SDO showing the front side of the eruption, and then I'll show a coronagraph image showing what got ejected from it. So here we're going to start with the stereo data. So this is going to show three different wavelengths. For the first two, you can see more of the structure, that dome that I pointed out first. And then for the third one, you can really see the prominence. So I'm just going to go ahead and play it, and I'll point out the eruption as it happens. So there's the dome just taking off, flying way out past the field of view. You'll see the same thing again in this wavelength. And you can see the prominence in the dark absorption here. Now here you'll see the eruption itself, and this part rises like it's going to erupt, but then it fails to, and it drains, but that material drains back down to the surface. That is the failed eruption. So you have two components. You have the successful part that shoots out, and then you have the failed eruption that rises up but doesn't quite make it and then drains back down to the surface. Here's the coronagraph. So this is from Soho, Lascaux, and you can watch, I'll let this loop a few times. The eruption itself is going to happen right over here as the movie loops again, just around the equator. And compare that to this large, well-structured CME that shoots off to the north. That's completely unrelated, but it gives you a sense of kind of the contrast between the two. You have this narrow, kind of weakly structured eruption that's happening from this event. And compared to that is this wide, well-structured, really prominent CME, very classic, to the north of it. So you can see that this structure was, our event was too wide for a jet, but it was too narrow for a CME, and it was poorly structured. So it's kind of in the middle there between what you would expect to see as a jet versus what you would see as a CME. And now here, this is the SDO data. This was processed especially by one of my co-authors, Angelos Forlidis, in order to bring out better detail. And I'll point out some of the salient features as the movie plays. So this is 171. You can see the dome taking off there. This is the part that makes the CME that you see that you saw in the previous slide. And here you can see this bright kind of vortex where the plasma is churning around in a loop before it comes down. We think that that's actually crucial to why the prominence did not successfully erupt. You can see it again here. The prominence is easily seen in the absorption, but you can see some energization happening along both the northern and southern legs of the eruption here. And the prominence material drains onto the opposite side from where it came up. And that's pretty unusual, except for this class of events. Now we'll see it in the 304, which is the coolest. You can really see the prominence in that here coming up. Here you see the prominence erupting. You see this getting very bright. That means that plasma is being heated. And now you see it extending, but see how narrow this structure is kept. It's because there's magnetic pressure on both sides of the prominence from the surrounding magnetic field outside of this structure that's keeping it narrow and confined. So the implications here, this event is not unique. We've found several others that have almost identical features. It represents an entire class of intermediate eruptions that are helping us fill in the medium area between the jets on one end of the continuum and CMEs at the other. It's helping us because we can now apply what we know about jets to CMEs. We know a lot about jets and how they erupt, and we can apply those same mechanisms in physics to CMEs, which will help us understand eruption triggers and help us move forward in predictive space weather capabilities. But the sun likes to keep things balanced, so it kind of gives with one hand and takes away with the other. It threw a wrench in the works with this failed eruption because we're not sure why that failed eruption actually occurred. It doesn't fit into any of our current theories. So while we can apply what we know about jets to the CMEs, this failed component of the eruption is raising a lot of eyebrows and is going to make predicting CMEs more difficult. So the main takeaways here are that this is called a Rosetta Stone event because it's bridging the jet to CME continuum. The space weather prediction is being complicated by the failed prominence eruption, but because the whole structure is pretty simple and symmetric, it makes it both a useful and a relatively simple simulation to make, a magnetohydrodynamic simulation, which we're actually already working on, and we'll be presenting those results in several months. So there's a paper related to this that's going to be published quite soon in the Astrophysical Journal Letters. The archive link to it is there. And if you have any questions or want any of the observations that I showed here, feel free to reach out to me at that email. Thank you.
Hi, I'm presenting research on the first eclipsing magnetic propeller in a cataclysmic variable binary. I am Peter Garnavich from the University of Notre Dame, and I've worked with several collaborators on this project. And I wanted to especially point out Colin Littlefield, also at Notre Dame, as he's created some movies on this work. Also, we use several telescopes, including the Large Binocular Telescope shown in the lower right of this slide, and Notre Dame is a partner in that collaboration. Muted myself. Okay. Normal cataclysmic variables are binary systems consisting of a cool companion to a white dwarf star. The red cool star donates mass that accumulates on the white dwarf. White dwarfs are dense end states of stars like our sun. They're extremely compact, having the mass of about the sun, but the size of the Earth. Generally, cataclysmic variables have orbital periods of hours. The cool star is so large and close to the white dwarf that a stream of gas flows to the white dwarf and forms an accretion disk, which eventually lands on the white dwarf. And there are cataclysmic variables where the white dwarf has a strong magnetic field. These are called polars or intermediate polars, depending upon the field strength. But in general, the gas lands on the white dwarf, sometimes having to move along the magnetic field lines. What I want to talk about is a propeller cataclysmic variable. Just as normal cataclysmic variables, there's a cool star that's donating mass to a stream heading towards the white dwarf. But in the case of a propeller, the white dwarf is both strongly magnetic and rapidly spinning. So as the gas approaches the white dwarf, it gets accelerated and ejected from the binary. Up to now, there's only been one propeller known in a cataclysmic variable, and that is AE Aquarii, which has a spin period of just 33 seconds. I always think, boy, it's the size of the Earth, but it's spinning every 33 seconds. That's a real stomach-churning thought. We have identified a second CV propeller, Lamos J0240, blah, blah, blah. It's the position of the star. We call it J0240 for short. So even better than being the second propeller, we actually view J0240 nearly edge-on in its binary orbit. So we see eclipses of the acceleration region, and for the first time, we directly observe the gas after it's been ejected by the propeller. Over on the right of this slide, you can see an illustration created by the famous astro illustrator Mark Garlick, depicting J0240, and this can be used when reporting on this work. So the acceleration of the gas depends on a number of things: the magnetic field strength of the white dwarf, the spin rate of the white dwarf, and the gas densities of the material approaching the star, all things we don't really know very well in J0240. But we do see the ejected gas, and that's moving out at 400 to 700 kilometers per second, or about 1 million miles per hour. You see in actually a calculation done for AE Aquarii back in 1997, this spiral pattern of the ejected gas, and that gas exceeds the escape velocity from the system, and so it just expands out into space like a large lawn sprinkler. It's been very dry here in South Bend. I've spent a lot of time watering my lawn. I've seen this in person. So both AE Aquarii and J0240 show bright flares in both its light curve and spectra. We can see that in the image on the right. This is a time series from the Large Binocular Telescope consisting of about 120 individual spectra covering an orbit, and then it's been repeated again to emphasize the entire orbit and its changes. And you can see these very short changes in the velocity of the hydrogen emission, and these are very fast, 3,000 kilometer per second flares, or about 6 million miles per hour, 1% of the speed of light accelerations of the gas. And we believe that happens when that gas approaches this rapidly spinning magnetic field. It really gets whacked by the field and then expands very quickly, gets shock heated, and then most of the rest of the gas continues on out of the system. But kind of like throwing a water balloon at a fan, it's going to hit the propeller blades, it's going to make a splat, and then a lot of the water is going to be accelerated out by the blades of the fan. We also see an important observation here: the narrow absorption of over half the orbit. You can see this dark line here. That is the actual ejected gas from the system that we now see in silhouette against the light from the stars and the flaring region. So we know J0240 is seen nearly edge on because of eclipses and this absorption. Okay. Also note the wiggly line here, dark wiggly line is absorption from the secondary star. We also see it moving around in its orbit and changing velocity in these spectra. So the origin and fate of J0240, we believe that it's a very rapidly spinning white dwarf with a period around 30 seconds. It was probably spun up by a period of very rapid mass accretion and a high mass transfer rate caused by the rapid expansion of the secondary star. We don't know that if this is a common thing in cataclysmic variables, but it seems to have happened in this case. That material brought mass and angular momentum to the white dwarf and spun it up. Once spun up, and now in a propeller mode, the white dwarf is ejecting gas, and that's taking energy away from the spin of the white dwarf. So in A Aquarii, we see it. In J0240, we suspect that the spin rate is slowing down and slowing down very quickly. So eventually the star will end up looking like a normal cataclysmic variable in maybe a 10 million year time scale. But we have not yet measured the spin rate in J0240. We're hoping to do that in the next observing season. We have a movie to help you visualize this. Colin Littlefield has created this, and it's available on the Notre Dame YouTube channel. You can see the secondary star, the red cool star, gas coming off of it, encountering this magnetic field shown as this kind of spidery set of dipole magnetic field lines getting flared and then being sent out of the system. So let's look at that. We're looking down on the system right now. We're going to slowly view the system from the orbital plane and show you that we do get the ejected gas like here, blocking our view, actually absorbing light from the system. And then after a while, that moves out, and then we don't see any absorption, and then we see it again half an orbit later. So this really shows you why we're getting this half an orbit of absorption line from the ejected gas. We also see the eclipses. So right about here, now we see an eclipse of that system, and we actually, yes, we see eclipses in the system. So I'll stop here. I want to point out that that this is only the second known propeller in a cataclysmic system. It's the first eclipsing propeller, and we actually, for the first time, see the ejected gas, and we measure its ejection velocity. And we think this is probably a short-lived evolutionary phase in some cataclysmic variable systems. Thank you.
Am I live? By far, the biggest problem for the most massive stars is the emergence of supernova imposters and giant eruptions. These events are enormous. They lose most of the mass of the star, given enough time, and no one understands them. Until their nature is understood, nobody is going to be able to make a realistic model of the evolution of a very massive star above 50 solar masses. No theorists predicted them, and they are quite mysterious. Almost all the known examples occurred in galaxies that are millions of light years away. We have, I don't know how many right now, a dozen possible examples. The one exception is Eta Carinae, which freakishly is only 7,500 light years away along the Carinae spiral arm of the Milky Way galaxy. This is the only supernova imposter or giant eruption survivor that we can see the details. Most people know a little about this story in astronomy. For 20 years, it was one of the brightest stars in the sky. It then faded from naked eye visibility. And in the process, it lost 10 or 20% of its mass. I mean, 15 or 20 solar masses was ejected. That left the star in a horrific state of thermal and rotational disequilibrium. Naive estimates suggest it should have recovered in about 40 or 50 years. It did not. Instead, it's taken almost 200 years to recover to its previous normal state. And equally odd, the recovery has been awfully unsteady, with paroxysms occurring about every 50 years. This is, as I said, the only available place to study the recovery of the internal structure of a supernova imposters. In 1999, using HST, we discovered an onset of rapid brightening that meant another of these paroxysms had just begun. Now, a twist to the story is that Eta Carinae has a companion star with a 5.5-year period. As we watch those stars come together, it's almost like doing a lab experiment where the parameters vary. You can't see the secondary star directly, but it provides all the ionizing ultraviolet light. And so as you watch the 5.5-year cycle, something happens near periastron. That's the place where the stars come closest together. And the spectrum temporarily changes, and the brightness temporarily changes. Now, we think we sort of understand this qualitatively. There are two stars. They both have winds. The winds collide, and they make a zone of shock fronts in between where the material has to flow out. The shock fronts prevent the two winds from mixing or intruding on each other. Now, for the spectrum that we observe in the star, it's important to notice that the hot secondary star ionizes a big part here of the primary wind, and that gives us high excitation spectral lines where atoms are ionized 2 or 3 times. A few weeks before each closest approach, gas dynamic stabilities destroyed the shock fronts. There is a reason for the past tense on the word destroyed. When the shock fronts were destroyed, in every event before 2003, something like this apparently happened. Without the shocks, material from the primary star could collapse onto the secondary, the hot little, it's not little, it's a really big star, but it's little compared to the primary, collapses onto the hot star and quashes the ultraviolet. And for that reason, the spectrum of the whole system changes because the ultraviolet can no longer ionize the outer parts of the massive star's wind. This idea, by the way, was contributed by Noam Soker about 10 years ago. Well, HST has observed 3 periastron passages, such as I described. The first one, 2003, fit the pattern that we knew about from previous experience that I just described. And I won't describe all the details in the spectra to you, but the point is, in 2014, the ultraviolet did not turn off at all. So we had to check it in 2020, and by golly, the 2020 spectra look just like 2014 and utterly unlike 2003. Sometime between 2003 and 2014, Eta Carinae's mass outflow, which previously was a record setter, became more normal, and it was too long to dump gas on the hot secondary star. So it's become almost a normal stellar wind. Other HST data agree. This is the only data on supernova imposter recovery. And there are two surprises listed here. The recovery took a lot longer than it was expected. And some kind of upheavals were happening in the star as it was out of equilibrium. So every 50 years, something came belching to the surface. In the next 20 or 30 years, it's going to change its appearance and end up being almost like Edmund Halley saw it in the year 1677. Years ago, the homunculus was just a fuzzy little nebula and the star wasn't much. Today, the star's become brighter than the nebula. It'll get about a magnitude brighter, and when it does, it will ionize the homunculus nebula. The homunculus look like a planetary nebula, but 100 times brighter and with a central star, 10, 30 times brighter. For more information, see this website, albeit it's got a little out of date.
I'm going to go ahead and share my screen. Okay. Hello, and thank you for tuning in and for making it to the last of this presentation series. My name is Luke Bouma, and I'll be telling you about work that we have recently submitted to the AAS journals. So canonically, most open clusters are thought to have sizes of a few dozen light years. Today, I'm going to tell you about an open cluster that we found is way, way larger. I want to start, though, with some context on how it is that star clusters form. Star formation, we think, is a top-down process. We start with giant clouds made of gas and dust, which are shown here in red. As the clouds collapse under their own self-gravity, filaments collide and overlap, and in the densest regions, we form clusters of stars. Many stars in the cluster are flung out within the first few million years. But the densest parts, for example here, can survive for much, much longer. As an example of what that looks like today, this is the open cluster NGC 2516. From corner to corner, this image is about the size of the moon. And when you zoom out, the cluster disappears into the night sky as a small blob. The Large Magellanic Cloud down here in the plane of the Milky Way are much more obvious to the eye. The surprising claim that in this work I set out to test is that our eyes are being deceived. Based on data from the Gaia satellite, a few groups have recently reported that the open cluster NGC 2516 spans 20 degrees on the sky, and that it's stretched over 1,500 light years in the plane of the Milky Way. I wanted to know, is this true? Is this open cluster in accordance with canon? Is it the typical 30 or so light years in size, or is it really 50 times larger? To understand the evidence for this structure existing, you need to understand the Gaia data. So Gaia measures the positions and the velocities of stars. And these other groups infer that the stars are related because they're moving in roughly the same direction at the same speed, along with being spatially close to each other. They did this, though, using unsupervised machine learning. So the idea is that if the data were the points on the right, you want the computer, the machine, to automatically label the different clusters in the data and to correctly separate them from the noise in gray. And the problem is that each group looked at the same data, but came up with different answers. So one of the groups found no evidence for the existence of the halo, while the other two groups did find evidence that it existed, but they disagreed on how big it was and on what its shape is. So it wasn't clear what to believe. Enter the Transiting Exoplanet Survey Satellite, TESS. TESS observes the entire sky, more or less. And so if we go back to our quarter sky view of NGC 2516, TESS observed all of its stars. So this background image is a composite TESS mosaic. And what we did is we looked through the TESS images and we measured how bright the different stars in the cluster were through time. This is what that looks like for 25 stars from the open cluster NGC 2516, where I have the hottest stars on top and the coolest stars on the bottom. The little wiggles that you see for any given star's light curve are from star spots rotating into and out of view on the stellar surface. And then what we do is we measure the duration between the wiggles to infer the rotation periods for the stars. We then put the rotation periods on the stars in the context of the cluster by analyzing how they change through effective temperature. Over time, we've known for a while now that stars spin down. And so in this diagram, they move up as they age. We've tested this previously for the open clusters, the Pleiades at 120 million years and Persepi at 650 million. The sun is way over the top of this plot because it's 4.5 billion years old. It's much older. For NGC 2516, this is what we find. The stars overlap with the Pleiades, which is not a new result. What is new is that we find the core and the halo of NGC 2516 overlap with each other. So gyrochronologically, they are the same age. Field stars don't show any evidence for this kind of rotational pileup. So overall, the story is a triumph, A, for machine learning, and B, for our ability to test the output that the machines give us. Previous work from the Gaia data suggested that NGC 2516 was at the center of a very long stream, but it wasn't clear how to interpret that because different groups were getting different answers. The conclusion of my study, based on the test data, as well as ground-based spectroscopy that I discussed in the paper, is that the halo of NGC 2516 is the same age as the core. There are some nice applications here in stellar and exoplanetary astrophysics, but personally, my favorite takeaway is that there are bound to be other enormous open clusters like this. This state might even be their default. Thanks for your attention.
All right, thank you all very much. We're going to run a little bit long because we got a late start. So again, I want to remind everybody to enter your questions into the Q&A box, and Susanna will read the questions. It looks like we have just one at the moment, but as usual, I have a few of my own, so we won't run out of questions. So Susanna, you want to take it away? What we'd like to do when you type something into the Q&A is please identify your affiliation in addition to your name.
So the first question is from Ethan Siegel from Forbes, starts with a bang, and it's a question for Emily. He asks, when you showed the video of the 2016 prominence event, is this perhaps an example of magnetic reconnection where the energetic component is simply not directed away from the sun?
Yes, so that's a great question. Thank you. It is a case of magnetic reconnection. Every time that you saw brightening in that movie was in fact reconnection happening and energizing the plasma. If you come to my iPoster, I can show you a little bit more data, but basically we believe that low energy reconnection is happening, and that why that failed might be because the prominence as it was rising, instead of reconnecting with open field where the plasma could escape and be a successful eruption, it was reconnecting with other closed field. And so it just streamed back onto the sun. So in a way, yes.
Great. Next question comes from John Martin, and it's for Kris. Since this work revised expectations for recovery of a massive star from a supernova imposter event, does that have any implications for when Eta Car might produce a supernova?
Hard to say. Eta Car's lifetime in the present stage of evolution is only a few thousand years. A lot of people had said that it already became a supernova, and the light just hasn't reached us yet. Remember, I said it's 7,500 light years away. I'm not sure that's quite what the question was, but does it match? Sorry, I'm having trouble here with the Zoom format.
Well, the question was, when might Eta Carinae produce a supernova?
And the answer is not before next Thursday, but not later than 10,000 years from now. One of the problems here is that because of the lack of understanding of the interior structure that I mentioned, it's really hard to say what its evolution state is. One thing we know about Eta Car, it is not young. It has helium-rich, cyano-processed ejecta on the surface, not in the center. So it's well evolved, but just how close to the end, we don't know.
If I could ask a follow-up, is there a general sense in the community who studies these stars that a supernova imposter will always eventually become a genuine supernova? Or is there something about them that could cause them never to become a supernova, but to flame out in some other way?
Well, this is bizarre. There's no reason why the thing that's left after an imposter explosion should not eventually become a supernova. And you've just heard me mention timescales of hundreds or thousands of years. The weird thing is that a few supernova imposters have become supernovae only a few years later. For those of you who know about supernova names, SN 2009 IP is obviously the name of a star that became a supernova in 2009, right? In fact, it became a supernova in 2012. And I don't know of any ESP or prognostication by the people who discovered it. It had a supernova-like explosion, and then it lived another 3 years before actually meeting its end.
Wow, okay. Well, Susanna, if it's okay, I'll ask a couple of questions while we wait. Oh, another one just came in, so I will defer. I will defer to the Q&A box.
This is another question from John Martin, unaffiliated. And this is for James. What happens to charged particles that are not moving at the resonant speed to be swept by the Alfvén waves? Are they trapped, i.e. the Van Allen belts?
Yeah, so particles that don't precipitate can actually bounce between Earth's magnetic poles. So charged particles spiral around Earth's magnetic field lines in what's called cyclotron motion. And they have to have enough energy or enough velocity directed along the magnetic field line to actually escape this bouncing motion. Otherwise, they just keep bouncing back and forth. And so electrons that aren't picked up and accelerated by Alfvén waves don't have that sufficient velocity along the magnetic field, and they just keep bouncing back and forth. So these are not electrons that are otherwise in Earth's radiation belts. The radiation belts are, Alfvén waves are believed to accelerate electrons, or they've been shown by satellite data to accelerate electrons between about 1 and 3 Earth radii above the surface, which is not a region of space that overlaps with Earth's radiation belts.
Okay, Rick, over to you.
All right. Well, my first question is for Jim and Greg, if you'd like. Now that you've confirmed what's actually happening here, how these electrons are being accelerated by the Alfvén waves, you've confirmed it in the lab. Does that improve the prospects for being able to confirm that the same thing happens out in space, or directly through direct observations?
I can take this one, Jim. So in fact, the technique that we used to demonstrate that we were seeing electrons that were accelerated by Alfvén waves was by using measurements of the electric fields and measurements of the electrons themselves and combining them with a new technique in order to see how the electrons are energized as a function of their velocity. That way you can tell whether something is catching the wave or the wave is simply passing by and they oscillate up and down and then the wave goes past. So in fact, this laboratory experiment essentially was a proof of principle that this technique works. And in principle, it may be possible to use spacecraft observations if they are measuring the electric fields quickly enough and the electrons quickly enough. So getting fast enough cadence of measurements that we may be able to apply the same technique to even existing spacecraft data, or perhaps upcoming spacecraft missions, which are making the appropriate electron and electric field measurements to actually demonstrate in situ, sort of in the Earth's magnetosphere, that we're seeing this kind of an Alfvén wave acceleration.
Okay, great, thank you.
I don't know if I could add.
Go ahead, Jim.
A couple extra thoughts from the laboratory side. When we designed these experiments, we scaled everything down in such a way so that we have every reason to believe, and we can back this up with our theory too, that the same dynamics are at work. So we're doing it in the laboratory. We're not directly observing precipitating electrons or the acceleration of precipitating electrons, but we're confident that it's the same forces at play in the experiment.
Okay. Did you want to go have something else?
I just wanted to add one more thing to him very briefly. Sure. It's the AAS meeting here. It's the annual meeting of the Laboratory Astrophysics Division, and really, one of the fundamental principles behind doing laboratory astrophysics, meaning that you're doing experiments in the laboratory that tell you about the physics of astronomical systems, is through a technique called similarity analysis, where one can take all of the length scales and time scales and multiply them together in such a way so that you can demonstrate that the physics, say in the Earth's magnetosphere, where the time scales are on the order of minutes and the length scales are thousands of kilometers, is corresponding to a laboratory experiment where the time scales are sort of microseconds and the length scales are on the order of meters. And it's really a triumph of physics that started with what's called the Buckingham pi theorem back in 1914, about how you can scale these things together and show that although these two systems have dramatically different length and time scales, you can take advantage of that similarity to demonstrate physics from one system is applicable to the second. That's all I wanted to say. Thank you.
Yeah, very helpful. Very interesting too. Thank you. All right, I have a question for Emily. What is the underlying reason, if we know it, why these different eruptions take different forms? Presumably it has something to do either with the structure of the magnetic field underlying the active region, or perhaps the strength of the magnetic field, or maybe it's both, or maybe I'm off target. But how does do the observations that you've made of this one particular eruption inform what's causing the different structures to occur?
Yeah, so the foundation of the continuum that we're filling in here is basically the areal size of the source region. So the larger that region is, for jets, you just have a tiny polarity that crops up, often in like a coronal hole. So you'll have a whole region that's like negative polarity. And you have just a little positive that crops up, pushes up from under the surface, and that creates the structure that gives you a jet, which looks very much like what I showed before, just a lot smaller. And for CMEs, of course, they commonly come from active regions, which are, you know, hundreds of times larger in area. So it seems there is a component of the magnetic field strength that we're looking into more carefully with the observations. But the most obvious thing that seems to determine which characteristics the structure gets is just the area, like on the sun, like looking at the photosphere of the structure that it comes from.
And so a follow-up is the size or the area of this Rosetta Stone eruption, is that also in the middle, kind of between when you see smaller regions producing jets and larger regions producing coronal mass ejections?
Yeah, this was in a highly decayed active region, so it was basically at the end of its lifetime. So it was definitely not a large active region at that point. There's even a little bit of debate as to whether we would even call it an active region anymore if it had decayed too much for that. But also the magnetic field had significantly weakened by that point. So yeah, I started out calling it the Goldilocks event because it was right in the middle of like every measurement you could take of it. It was in the middle.
Rick, can I ask a quick question of Emily as well?
Yes, and then we got another one that came in on the Q&A.
Yes. So I was wondering, you had mentioned that this is interesting because it kind of allows us to apply our understanding of jet formation to CMEs. Is this paradigm shifting, or were we already kind of modeling CMEs in that way?
It is a bit shifting. The idea of a jet to CME continuum isn't totally new. We're just kind of filling in the middle of it with this discovery, but it's more that it's a direct correlation that you can see. Like you get something that looks like a CME here, but without the structure, which helps explain one of the problems space weather people have been struggling with is why some CMEs have that beautiful bubble structure and other ones don't match up. They have less structure, they go in a different direction than you expect, different things like that. So this could help kind of answer those questions.
Thanks.
Yeah.
So we got a question that came in from William Waller, unaffiliated. This is also for Emily. What roles do the exterior magnetic field pressures have on the eruptions?
That is great. So to the north of this event was a polar coronal hole, which is just open field, meaning that one end is connected to the sun and at the other end is connected somewhere out into the solar system. And south of it was a helmet streamer, which is just a really big loop on the sun. Both ends are connected to the sun, but at a great distance from each other. So, and both of those structures were kind of pushing in on it. So like when I pointed out how narrow the prominence eruption was, that's what was keeping it narrow, we think, was that it was getting the pressure from the coronal hole pushing down on the northern extent and the helmet streamer pushing up on the southern extent, kept that prominence narrow in its rise rather than kind of bubbling outwards into a more like CME kind of bubble shape.
Okay. I have a quick question for Peter Garnavich. So it's always hard to generalize from an example of one, but now you have an example of two. So I'd like you to generalize if you could and tell us how common you think this phase of evolution in a CV might be. Do you think it's just, you just got lucky and found a couple that are, you found a couple of events that are inherently rare, or do you think that a significant number of, or a significant fraction of cataclysmic variables go through a phase like this propeller phase?
Well, I guess rare is a tricky term here, that it might be a common phase that just doesn't last very long. And we see for Aquarii, which is very similar to J0240, that its spin down rate is, it has a time scale of 10 million years. Probably J0240 is similar. and that's not a very long time scale for astronomical objects. So, we're looking into how similar these two are. The Aquarii has this very interesting chemical abundance ratio, carbon to nitrogen, that suggests that it really got down to the core of the secondary star during this mass transfer, and we want to find that out with JO2402. Well, most other CVs don't have that odd mass abundance ratio, so they could also just be rare beasts, and not only rare but short-lived. So maybe there aren't too many of them out there.
I'll ask you again when you have 3 of them.
Well, keep looking.
And finally, a question for Luke. What causes a cluster to spread out in basically in a long line instead of, just sort of drift away into a cloud, more cloud-like or more spherical structure?
For sure, yeah. So that's a good question. The current theories for what could produce these sorts of strings or spaghetti aspect ratios for these open clusters are 2. The first is that these are tidal tails, and the second is that some of that structure is primordial. It comes from the giant molecular cloud not being spherical but being filamentary. So in the tidal tail explanation, the idea is, as the stars escape out due to the galactic tide, then differential rotation inside of the galaxy itself is what produces the leading and the lagging arms. So the stars that get ejected interior to the cluster inside of the galaxy are going to move a little bit faster, and the ones exterior are going to move a little slower. So over time, you can produce the leading and the lagging arms. I would say that that's the favored explanation for the structure that we're seeing in this open cluster. But the other idea that some of it could be primordial might be necessary to explain some other streams that have been observed. Particularly, there's a stream called Pisces Eridanus that my co-author Jason Curtis led a paper on 2 years ago, and that's a case where we might need to invoke slightly more exotic progenitor cloud structures. So, but the answer is we're still not sure what the origin is for this one, and back integrating the orbits isn't yet possible. And it may not be for reasons I'd be happy to discuss.
Okay,
Can I ask a follow-up to that?
Please.
Do you have any plans to look for similar extended structures around any other open clusters?
So personally, the answer is, well, sure, I can go ahead and say it's not a big deal. Yes. So this particular one that I looked at was the one that I chose because the data were immediately available to do the analysis. But there are currently now something like a dozen open clusters within the nearest 500 parsecs or so that have these kinds of extended structures reported based on the Gaia data alone. And so the kind of verification analysis that I did to confirm based on rotation periods and based on spectroscopy whether or not the extended structures are real can easily be applied to these new cases from the Gaia data as well. And I expect to be doing some of that work. I'm sure other groups will be doing it as well.
Okay, well, thank you. All right. Well, I want to thank all of you again for your presentations. I want to thank the audience for joining us today. I am aware of press releases for most, if not all of these, and I will link to them from the online press kit during the course of the next couple of hours. And you should look on Eureka Alert or elsewhere if you want to get a hold of them sooner. I want to also thank the University Space Research Association, USRA. You see their logo behind most of us. They've been sponsoring the press office for the last few meetings, and they help offset the cost of doing these Zoom press conferences, which I appreciate. The next press conference is this afternoon. Well, for me and East Coast time anyway, it's this afternoon at 4:30 p.m. Eastern. You can do your own time zone conversion. And the topic of that one is black holes and active galactic nuclei. And with that, I will thank you all and see you hopefully in a few hours. Bye-bye.